Easy, a plug-and-play educational system, is portable, compact and a complete system for microstrip sensor characterization. The system has been designed to introduce students in the basic concepts of microstrip silicon detector, widely used to track the trajectory of particles in high-energy physics experiments. In the video radiative source exercise, you can find a full description on the system and the introduction to the concepts of pedestal, noise, cluster and signal reconstruction, charge collection and depletion voltage. In this video we will investigate the structure of the microstrip detector, how the charge is shared between adjacent strips, and the determination of the depletion voltage and charge collection using a laser source. The components of the EASY systems are the control unit and the sensor unit. The control unit is the heart of the system communicating with the sensor unit and the computer software. It contains the data acquisition control, and it is also in charge of processing of the sensor data and trigger inputs. In addition, it contains an adjustable height voltage unit for microstrip sensor bias, with voltage and current display. The control unit communicates with computer software via USB. The sensor unit accommodates a P-on-N silicon microstrip sensor, the same type of sensor used in Atlas detector at LHC. P-on-N strip detectors consist typically of an around 300 microns thick N-type bulk. On one side, a thin layer segments form strips out of P-type material, whereas the back implant is N+. An oxide layer lies on top of the implanted strips which prevents the leakage current flowing directly to the readout electronics. The signal from each of the strips is capacitive coupled to a metal strip made of aluminum, lying directly above the P-strip implants, and the charge is read out through this ohmic contact. The EASY silicon microstrip sensor is segmented in 128 strips with a 160 micron pitch, while the metal strip width is 44 microns. The abrupt junctions are formed between the strips and the bulk silicon. The depletion zone grows from the strips to the backplane so that the device can operate partially depleted and the movement of holes forms the signal. EASY system incorporates a 980 nanometers pulsed laser to induce charge in the microstrip sensor, mimicking the passage of a charged particle across the detector. The penetration and interaction mechanisms of photons of laser light differ in several aspects from ionizing particles. With a laser beam the charge is generated within the full volume traversed by the photon pulse, and the energy deposition decrease exponentially. While a minimum ionization charged particle deposits the energy uniformly along its trajectory. On the other hand, a laser beam does not produce secondary electrons as a charged particle, which normally increase the cluster size, making the laser beams ideal to prove the structure of the microstrip silicon sensor. The laser beam is held in the control unit and connected to the sensor unit by means of an optical fiber. The mobile part of the sensor unit contains the laser lent. The two micro-positioners screws allow to movement the laser lent in 10 micrometer steps, horizontally and vertically, to focus the laser and to move the laser beam over the sensor. This moving part must be placed so that laser beam is aligned with the microstrip sensor. To start the exercise, we connect the control unit to the sensor unit through the flat cable. The flat cable transmits, amount other, high voltage to bias the microstrip sensor and reference voltages, and collects the signals from Beetle chip. The Beetle chip, developed for CERN LHC experiments, is in charge of the readout and amplification of the signal of the microstrip detector. The EASY control unit is now ready to be connected to the computer via USB. After power the control unit, the bias voltage should be set to 110 volts, well above the depletion voltage. The depletion voltage was determined in the radiation source exercise described in our previous video. We are now ready to start the data acquisition software. The control unit is able to generate a pulse that is used to trigger the laser system. Prior to start taking data, the system has to be synchronized. The laser synchronization scans the delay between the pulse sent by the control unit and the data acquisition so that the system can sample at the maximum of the signal produced by the laser. The delay corresponding to the maximum of the peak is 100 nanoseconds. Once the delay has been set, we can proceed to focus the laser. The laser beam is focused using the two micrometric screws that move the laser up and down over the microstrip detector and in the horizontal plane, perpendicular to the direction of the strips. The focusing is an iterative process. We should to be aware that laser beam is reflected in aluminum strips. So, if the laser beam incisors over the strip, no charge will be collected. In this case, we will need to move the laser beam away from the strip. We can start a laser run and observe the charge deposited in each strip by activating the Event Display tab of the Acquisition Data program and selecting the Signal button to subtract pedestals and common noise. Then, we will move the laser lens in the horizontal and vertical direction till some signal over noise is observed. Once some signal is observed, we start a more fine-tuning process by moving the laser slowly up or down till the signal reach a maximum. To check that the laser beam is correctly focused, move left or right the laser beam to observe that the collected charge moves from one strip to the next one. And at some point, disappears when the laser incised over the aluminum of the strip. If at this position, the signal does not disappear completely, you move up or down again the laser length till non-charge is observed. Once the laser is properly focused, the study of the strip's structure can be initiated. We start for an initial beam position, for instance, 0 charge in strip 40, and we measure the charge in the adjacent strips, strip 39 and 41. The charge can be measured by downloading the data to file and calculating the mean charge collected by the strips after pedestal and noise subtraction, or for a faster study, by placing the cursor over the graphic and estimating the collected charge. In this initial position, since laser beam is reflected in the aluminum strip, a charge compatible with the electronic noise should be observed for all strips. From this initial position, we take several laser runs moving the laser beam right in the horizontal plane in steps of 10 micrometers, measuring the charge in the 3 selected strips. We will observe, when the laser moves away from the center of the strip, charge begins to appear on the strips 40. This is due to the fact that part of the incident light is still reflected on the aluminum. If we keep moving the laser beam, the charge on strip 40 will increase. When the beam falls between the strips, the charge will be shared between strips 40 and 41. If we continue moving forward, strip 41 will start collecting more charge till reach its maximum. On the other hand, the charge collected by strip 40 will decrease till become compatible with electronic noise. We will continue this process moving the laser, right and left, for the initial position, towards strip 41 and towards strip 39. By plotting the charge collected by 3 adjacent strips, we can illustrate how the charge is sharing between strips and prove the strip structure. The colors of the curve correspond to the charge collected by each strip for every laser beam position. We can also determine the strip width for the laser path without collected signal. The beam spot will be measuring from the distance between the position when the laser beam starts generating charge in the detector and the maximum of the charge. And finally, the microstrip pitch will be the distance between 2 minima of collected charge. Using the laser beam, the growing of the depletion zone with the bias voltage and the laser penetration depth can be studied by recording the charge collected for various bias voltages. The measured charge will be a convolution of the extension of the depletion zone and the energy deposition within the silicon. Since the laser energy deposition is exponential, the laser beam could stop in the detector bulk. The laser penetration depends on its wavelength. By measuring the charge collection efficiency, defined as the fraction between the measured charge for a certain bias voltage and the charge at the plateau, when the detector is fully depleted, the laser beam penetration can be calculated. Depending on laser wavelength, the charge collection efficiency has different shapes. The longer the laser wavelength, higher is its penetration and the closer to a minimum ionizing particle. Before starting the data acquisition, we fix the position of the laser beam so that the charge is shared between 2 strips. In this way, we make sure to collect all the charge deposited by the laser beam, avoiding any reflection on the aluminum. The charge distribution has a Gaussian shape. The mean charge can be calculated by downloading the raw data to a file and fitting the charge deposition after pedestal and noise subtraction and cluster reconstruction. For a fast analysis, the cursors can be placed on the top of the distribution to get an approximated mean charge. We measure the charge for different bias voltage to obtain the characteristic curve of charge collection as a function of the bias voltage. The plot shows how the charge collected grows with bias voltage till a plateau is reached when the sensor is fully depleted. From the graphic, the depletion voltage can be estimated, defined as the bias voltage applied to reach a plateau, meaning that the depletion area has reached the full detector. Dividing the collected charge by the charge of the plateau, one can obtain the charge collection efficiency as a function of the bias voltage. And by fitting the curve, we obtain that the laser penetration depth is 164 micrometers. For more detailed information, you can consult the activity book for students. The book provides a full description of easy device, data acquisition system, and all the details of the exercise proposed in this video. For more information about the Educational Alibava system, please contact us.